A segment with endpoints on a circle is called a chord. So a chord has 2 points that are on the circle, whereas a radius does not. A radius has 1 point on the circle and 1 point at the center of the circle. A diameter is a special type of chord. So there's a theorem that reads congruent central angles have congruent chords. So what this looks like is if you have a circle and you have this angle, this is called the central angle, and you have this angle, these two are vertical, that they have congruent chords. So this segment would be equal to this segment. This red chord would be equal to this red chord. The second part of the theorem is congruent chords have congruent arcs. So if you know that this chord is congruent to this chord, then, that's the center, then their arcs are congruent. So this arc would be equal to this arc. And number 3, congruent arcs have congruent central angles. So congruent arcs, so if you knew that this arc was congruent to this arc, then the central angle that makes up the arcs are congruent. So we'll go again with some vocab. So a central angle is an angle that is made by the center and radii. This is a central angle. A chord is a segment that connects 2 endpoints on a circle. And an arc is the curvy part of a circle. So we'll use this theorem to answer these questions up here. So solve for the variable a. So what I could do for this one is I could draw in the radii, because I know that the radii are all equal. So these blue segments are all equal. Oops. So if I know that these 2 blue segments are equal, this triangle is an isosceles triangle, and this triangle is an isosceles triangle. And let's see, I know that this side and this side are both 9, and this is making a right angle and this is a right angle. So technically these 2 triangles are congruent by HL. Do you remember HL? So hypotenuse and leg. So all 3 of these triangles all 4 of these triangles are equal. They're right triangles. So that means that this segment by CPCTC, congruent parts of congruent triangles, this segment has to be equal to this segment right here. So I could figure out what this side of the triangle is. Actually, this side is 12.5. It's pointing to it. This whole thing is 12.5. So A has to be 12.5. And then this segment over here kind of goes along with the same thing. So I'm going to draw on the radii again so we can see it. And again, I have this side's 36, 18, 18, 18, 18, a 90-degree angle. These sides are all equal because they're radii. So that would mean that if this segment is 16, then this segment has to be 16. So this one's 16 as well. And then the next part, theorem, within a circle or in congruent circles, chords equal distant from the center are congruent. That's kind of actually, that goes along with what we're doing right here. Chords equidistant are congruent. So, let me see. So the converse is congruent chords are equidistant from the center. So over here we kind of did the proof of it. If we know that these chords are congruent, then they have to be equidistant from the center. This is the shortest way to get someplace is perpendicular. So that's why we have this 90. That's why these two are equal. So we kind of, with this problem, just prove the theorem down here. So these two are the types of problems that you'd run into. In a circle, a diameter that is perpendicular to chord bisects the chord in its arc. So if this is 90, then these two are going to be equal. If we know this is 14, this has to be 7, and this has to be 7. And then you could do the Pythagorean theorem to find what r is. Theorem 12.7. In a circle, a diameter that bisects a chord is perpendicular to the chord. So if we know that these two are equal, it's like the converse of it, then this has to be a 90. And then in a circle, the perpendicular bisector contains the center of the circle. So this segment is the perpendicular bisector, and it's going to go through the center. So basically it's saying as soon as you know that either these two segments are equal or this makes a 90, then it has to go through the center. So we could figure out what y is by doing y squared plus 11 squared equals 15 squared. We could figure out what r is by doing 7 squared plus 3 squared equals r squared. So down here, find the length of the chord. So remember, the chord is this length. So to find x, what I would do is I would take this right triangle and I would do 4 squared plus, let's call this short one y squared equals 6.8 squared. Once you solve for y, double it, because twice y equals x. That's how you can figure out what x is. And then down here we're just using these properties or all these little tiny theorems. We're applying them. So if AB is 20 and the radius is 15, if AB is 20, then this has to be 10, and these are 15. And CM is equal to x. You're finding x. So you're going to use the Pythagorean theorem. 10 squared plus x squared equals 15 squared, and solve for x. So x squared equals 125. X equals the square root of 125, which is 5 root 5, and no units. And then number 2, we have AB, it's a chord, it's 24. This whole thing is 24. But this segment's perpendicular. It's going through the center. So it means that these two are equal. So this has to be 12, and this has to be 12. And CP is 12. I'm thinking P's right here. So to find CA, you would do 12 squared, plus 12 squared equals x squared, and solve for x. So CA is what you're trying to find, and this segment P is right here. AB is all the way across. This has to be 12 too. And then now we're going to do CP is 5. The radius is 9, so the segment that's the radius is right here. That's 9. And AB all the way across is x, this distance. So what I would do is I would find y first. So you're going to do y squared plus 5 squared equals 9 squared. Y squared equals 81 minus 25. And then once you get what y is, you double it to figure out what x is, and make sure you rationalize or simplify the square root.